All right, this is example 2.8 from the Smith and Van Ness 8th edition textbook. We worked this in class, but I wanted to go over it maybe in a little bit more detail in this format. It says calculate the internal energy and enthalpy changes resulting if air changes from initial state of 5 degrees C in 10 bar with a specified molar volume to a final state of 60 degrees C in 1 bar. Assume also that air remains a gas for which PV over T is constant, and you are given the CV and CP values. So the first thing I'm going to do here in MathCAD, I need to define bar as a special unit, and so I define that as 10 to the 5th pascals. I give my given information as far as properties, and then for these problems, if I want to, I can draw a PV diagram, but sometimes I find it's just simpler to do initial state and final state. And so I have my initial state. My version of MathCAD does not do degrees Celsius, it only does absolute temperatures, and so I convert everything to Kelvin. 10 bar, and here's my initial volume. My final state, 333 Kelvin, and 1 bar. And then I write down what we need to find, and that is the delta H and delta U. And so I went over this in class, but I want to go over this a little bit more here. And so note that we are not told anything about this process. We do not know how this process is accomplished. We do not know if the process is reversible or not. We do not know how many steps are in this process. All we are given are the initial and final conditions, and all we are asked to calculate is a change in enthalpy and internal energy. And so what this should do, as you are getting better at solving these problems, what this should do is trigger in your mind that what we are asked to calculate, delta H and delta U, those are state functions. Those are state functions, and those only depend on the thermodynamic state of the systems, and they are path independent. And so if you remember from your book, I mentioned this in class, there's a little section on page 43 that's bolded that I think you should make sure that you pay attention to. It says, for the calculation of property changes, but not for heat and work, an actual process may be replaced by any other process that accomplishes the same change in state. This choice is made based on convenience, with simplicity a great advantage. So what this, and this is given to you right after they go through all these derivation of formulas where they want you to calculate Q, W, and delta U and delta H, specifically for constant volume and constant pressure processes. So what students that aren't real sure about what to do, what they'll say is, well, I've got pressure and temperature and volumes changing. How in the world am I going to have to be able to calculate delta H and delta U? I don't have constant pressure, I don't have constant volume processes. Well, the answer is, since we don't have to calculate Q and W, we only have to calculate delta H and delta U, we can figure out any other process we want to accomplish the same state. And if you look at the solution that your book does on page 46, what they do is they divide this process into 2 steps. They divide it into a constant pressure and then a constant volume process. And so that makes sense because the textbook in the pages before told you how to calculate delta H and delta U for constant pressure and constant volume processes. But that means you have to divide it up into 2 steps. If we look at page 43 again, and this time it's, I believe it's towards the bottom of the page, they have this little paragraph here that talks about for a reversible constant pressure process, you get delta H is equal to the integral of Cp dt. But then, notice what they say. They say because H, Cp, T, and P are state functions, this equation which is equation 221, or 222, which is basically the same thing. I'm talking about this part here. The delta H is equal to this integral of Cp dt. This equation here, forget about the Q right now. This equation here applies to any process for which P2 equals P1, whether or not it is actually carried out at constant pressure. So what this means is that because this is whether or not it is actually carried out at constant pressure, what we can do is we can calculate delta H directly from this problem statement without having to come up with multiple steps in this process. And so the easiest way to do this is just to calculate delta H is equal to the integral of Cp dt. So that means Cp in this problem statement is constant, so that means we can pull it outside the integral. We integrate dt from T1 to T2, and that's just delta T. And so the delta H for this entire process, going from our initial conditions to our final conditions, is 1601 joules per mole. We can do the same argument for delta U. Delta U, CV, and T are state functions, and so we can calculate delta U is equal to the integral of CV dt, or CV delta T, because CV is constant, and so delta U is equal to 1143 joules per mole. And note, when I use MathCAD, I usually have the I usually have it use scientific notation once you reach a threshold of 1,000. That just is a little bit easier for me. So those are very simple calculations, and it's very difficult to make a mistake there. But let's look at what your book did. Your book kind of took the long way around this problem. So what your book did, just to review, they came up with two different processes, or two different steps to accomplish the same process. The first thing they did was a constant volume cooling to the final pressure, and then they did a constant pressure heating to the final temperature. Now, if you look at the original process, the process was going from 5 degrees C to 60 degrees C. You know, to me, when I look at this, why would I want to cool first and then heat when I want to heat to begin with? That's just something. Sometimes in thermodynamics, you can come up with these things to model these processes, and we don't usually have to worry about practicality. Sometimes that's good, sometimes that can be a little confusing, but that's how it is. So I'm going to put down all the information then for this first part of the process, constant volume cooling to the final pressure. So again, I make my little table for initial conditions and final conditions. I've got V1, T1, and P1 are given. P2 is known, that's 1 bar, that's the final pressure. V2 I know is V1 because it's at constant volume, but turns out we're going to have to solve for T2. We don't know what T2 is. So we have to use the information that's provided to us in the problem. PV over T is constant, and so if you want to let MathCAD do the algebra for you, what I did was I set P1 V1 over T1, control equal, is equal to P2 V2 over T2, and then I ask it to solve for T2, and you get this expression here. And T2 ends up being 27.8 degrees Kelvin. This might be something else that, if you start to think about it a little too much, may cause you some problems, but it's something that, fortunately or unfortunately, depending on how you look at it, thermodynamics doesn't really care about. This is a really low temperature, really low. In fact, at 1 bar, which is the pressure that we're at, air turns into a liquid at 78, almost 79 degrees Kelvin. So this air is liquefied. Is that a problem? Not really, because we're dealing with a theoretical process. This is not a real process that we came up with to accomplish this change in state. And so we We don't have to worry about calculating latent heat of vaporization, so on and so forth. But you know, what I would say is this is kind of something where sometimes in thermo you got to kind of turn your deep thinker off, or turn it down a little bit, and realize that we're just making up this theoretical process to accomplish this change of state, and let's just go on and keep crunching the numbers. So anyway, once we have T2, we can calculate what? This is a constant volume process, so we can calculate delta U for this is CV delta T, and so we get a negative 5203 joules per mole. And that makes sense because we're cooling. We are really cooling, right? We're cooling at over 200 degrees C. All right, what about the delta H? This is a constant volume process. We can calculate delta H. The way your book does it is they use the definition of delta H is equal to delta U plus P delta V plus V delta P. Since delta V is 0, this term goes away, and we're left with delta U plus V delta P, and we get this answer minus 7284 joules per mole. Again, it's negative cooling. That makes sense. Question I have for you, could we have also used for this step, for delta H12, could we have also used CP delta T? And you can see the answer is yes. And why is that? Well, the answer is yes, because we're just dealing with state variables, right? State functions again. And so we can just use delta H is equal to CP. We don't have to worry about this P delta V, V delta P, and so on. Once we had T2 and T1, we could have calculated delta U as CV delta T and delta H as CP delta T. But sometimes it's good to have more than one way to calculate things. And so if you wanted to, we could do the calculation. We could also write delta H dot 1 2 delta H dot 1 2 is equal to C dot P times T2 minus T dot 1, and delta H dot 1 2. We get the same answer. Yeah, within rounding error, we get the same answer. And again, this is joules per mole. So that gets the numbers in with the right units. So same answer. That's a good way to check your work. You're free to use whatever you think is more convenient. All right, now the next step of this process is constant pressure heating to the final temperature. And so let me bring all that over. So we go from the P2, V2, T2, which are given here, to our final state, P3, T3. We know that it's constant pressure, so P3 is P2. T3, that's our final temperature. We know what that is. We don't know what V3 is. So again, we're going to have to solve for V3, right? We're going to have to solve for V3, and we do that using the given information. Since this is a constant pressure process, we can then calculate delta H. Delta H is equal to CP delta T for constant pressure process, and we get 8885 joules per mole. Now we can calculate delta U. Again, you have two options for calculating delta U. You can do what the book did and kind of pretend we don't know that delta U is a state function, and we can use this delta H equals delta U plus delta PV. Solve for delta U, and we get 6347 joules per mole. We could also have used delta U dot 23 is equal to CV times T3 minus T dot 2. And we get delta U dot 23. Is that the same answer? Yep, that is the same answer within round off error. So it's joules per mole. All right, so again, more than one way to solve that little calculation. Now that we know delta U for both steps and delta H for both steps, we can then add those together and we get the delta H overall. Delta H overall is 1601 joules per mole. Delta U overall is 1143 joules per mole. Let's check that with what we had with a very quick, simple method. Same answers. Same answers. Up here, we just did one calculation. Down here, the way your book did it, we had to do multiple calculations, but we got the same answer. And so this brings up some notes that I want to go over. It took a lot more work to solve the problem by constructing the two theoretical steps that your book did to accomplish the same process. It also introduced some kind of ambiguities and questions that we had about air liquefying. But if we understand what state functions are and how changes in state functions can be calculated, we were able to save a lot of time at the beginning of working this problem. So what I would encourage you to do, make sure you understand the context behind all these formulas that are in your book. When you read the book and you review the material in the chapters, don't just skip all the text, because all that text is there for a reason. And while some of it may not seem as important, there are certain phrases, sentences, and paragraphs in there that you really need to make sure that you understand. Because if you do, it can save you a lot of time and effort, and you will also, with all these calculations, punching these into your calculator, you're a little bit more prone to make a mistake than if you just did delta H is equal to Cp delta T for the overall process. The other thing that I'd like to point out is that for a lot of these problems, getting the answer is kind of like a state function. There's sometimes more than one path. There's more than one way to solve these problems. And so, if you know, the more you know, the better off your chances are going to be that you're going to pick the most efficient path. But also, what you should realize is that you can use these other pathways to check your answer and make sure that you aren't making mistakes.